Yeah, so again, Nuo Li, together with Joe Race from Department of Mechanical Engineering, Boston. The presentation is about SDT fan alone RAM simulations using SU2. The floor is yours, Neil.
Thank you. My name is Noah Li. I am a PhD student from Boston University, and I'm presenting some work related to a steady RANS simulation validation attempt using the SDT fan. The other co-author is Professor Cheryl Grace at Boston University Department of Mechanical Engineering. I'll briefly introduce to the configuration. The SDT is scaled down to the engine. It's a 22-inch diameter fan rig tested at the NASA Glenn Research Center's 9x15 low-speed wind tunnel. And the experiment data is taken at several operating points, and different types of data was collected, including the far-field acoustic, which is the primary interest in my study, and we have been using it as a basis for validation in many past studies. And in addition, stator unsteady pressure is measured, and fan wake flow is also measured using both LDV and hot wire. So in this talk, I will only focus on comparing the SU2 solution to the hot wire measured data at the approach speed, as it gives the most reliable measurement for the turbulence quantities. So in this talk, I'll explain the simulation domain, mesh, and the solver configurations, and then I'll show some comparisons, both qualitative and quantitative. So in this rendered image, shaded area is the simulation domain. We assume that the inlet inflow is axis symmetry. So we only simulate one single passage, and the stator is not included in the simulation, as in our project we're mostly interested in the time average wake flow and turbulence quantity upstream of the stator. So in summary, it's a single passage rotor along simulation, and the domain is being simulated in a rotating frame. This is a zoomed in image for the simulation domain. And at the inlet and outlet, the Giles boundary conditions is used. The total pressure and total temperature is prescribed at the inlet that matches the ambient condition, and at the outlet, static pressure is prescribed, and that is calculated from the measured total pressure ratio as well as the isentropic relations. And in between the passages, the periodic condition is set. And on the blade surface, including the blade tip and the spinner, which is the rotating part of the hub, the zero heat flux condition is used. And for the shroud and the downstream hub, these are the stationary part of the wall. So I use the shroud condition, and also the R zero heat flux non-slip condition. So for the mesh, which is a multi-block structured mesh created using pointwise. There are 12 blocks in total, and they're being treated as a single structured block in SU2. Okay. So these figures here are examples of the mesh at different locations. The first figure is the shroud surface, and again, the colors highlights the quadrilateral domains that defines the structured blocks. And the second figure is the blade surface with refinements near the leading edge and trailing edge, as well as the blade tip. And third figure is the tip gap. So the tip gap is a 0.5 millimeter and includes 27 points in radial direction. The RANS equation solver is used in SU2, and the second order upwind reconstructed road scheme is used for the space, and Euler implicit method is used for time integration. And the Venkat 1 limiter is used for the flow solver. And the SST turbulence model is used, and also the second order upwind scheme is also used for the turbulence convection and with Euler implicit method. The wall distance limiter was employed, and this was found to be the only that works in my case without blowing up the simulation. And the solution is initialized using fully axial flow, and the mark that matches the expected inlet condition. And again, the inlet and outlet conditions are determined by the measured total pressure ratio and isentropic relation. And the goal is to match the experiment mass flow rate. A constant dynamic frame velocity is used, so there is no ramp, and the turbulence intensity is set at 1%, and the viscosity ratio of 1 is used. And although the intensity matches the experiment condition, but the velocity ratio is lower than what many other people used, which usually range from 2 to 40 at the inlet for this application. But in my own experience, a larger viscosity ratio tends to blow up the simulation in this application. So I will compare solution at two hardware survey location. The station 1 or hardware 1 is the mid-gap location, and the station 2 is the location near the design stator leading edge. So moving on to the result, a quick summary here. Both inlet and the outlet mass flow rates are conserved, matching the experiment within 1% error, and the total pressure ratio is also in good agreement with the experiment. We have tested two grid versions, and results are actually very similar, so I'm only going to show the final grid solution. Starting with the qualitative comparison. The color plot here represents the streamwise velocity at two hardware survey location. Left column is the SU2 solution, and right column is the experiment. And also note that boundary layer is not measured by the hardware, so the probe wasn't moved all the way to the wall. So the shaded gray area here are not included in the experiment measurement. And qualitatively, the wake width and the wake shape are functioning pretty well between the SU2 and the experiment. And next, moving into a more quantitative comparison, the plot here are passage values probed at the midspan location at two hardware locations. The first column is hardware 1, and second column is the hardware 2 further downstream. And the horizontal axes here are percent passage. The red solid line is SU2, and black dashed line is the hardwire time average mean passage value. The values are centered to match the velocity deficit center. Overall, the velocity, turbulence, kinetic energy are in reasonably good agreement with the experiment. Before going into the average comparisons, I'll briefly introduce to what we're interested in. Our field, the broadband interaction was between the rotor wake and the stator. Result, but briefly introduce. So for the interaction rates, usually it can be solved by LES time signal, or we could use a cost rent-informed analytical model. So this will be our case. Model usually requires flow field output of the state as input. So therefore, inputs that are required, the velocity components are straightforward time average. The turbulence quantities, turbulence intensity and turbulence length scale are of most interest, and these values are being used to define the inflow turbulence spectrum and the statement. So for the so I'll compare these quantities between the CFD and the experiment. So for the CFD, the turbulence intensity or U prime is found by assuming isotropic turbulence. Turbulence length scale, I call it lambda here, is found using the Pope's formula related to the turbulence kinetic energy and turbulence dissipation rate. This tested in our previous found to work very well most of the cases. In the experiment, the intensity is found in the parametric velocity and the length of lambda. Now using the time correlate assuming that the turbulence is frozen. So these comparisons here are average across circumferential direction. The vertical axes are percent span. 0 will be at the top and 100 will be at the shroud. The first plot is the stringwise velocity, and the second plot is the RMS velocity, or the dimensional turbulence intensity. The vertical axis, well, sorry. So in the SU2 and the experiment compares comparisons showing pretty good agreement in time average velocity and U prime. But on the other hand, the turbulence length scale comparing between the Harvard camcorder values and SU2 results are showing that the post formulation is showing that the SU2 underpredicts the length scale. Um, and we found that this is mostly due to a large dissipation rate omega in the SU2 solution. And in our internal study, we have compared the SU2 solution against another CFD code, but I'm not allowed to show that here. But we found that the omega prediction used in SU2 is, especially at the background, is larger than the other CFD numbers. This is believed mostly due to the large inlet viscosity ratio. Sorry, a small inlet viscosity ratio. But my own experience, a larger viscosity ratio of the inlet is to blow up the simulation, but we're still looking into this. I'll quickly go over a few lessons. So for this particular application, a small y plus less than 1 is preferable, and large element length ratio or element growth rate should be avoided. So these are just common criteria for wall resonance. And we also found that implementation of trying to solve the turbulence correction is the wall distance limiter, which is a progressive version of the patch limiter. And we also found is most in 10 to 100, while the larger CFL number higher than 100 tends to blow up the simulation at the beginning. But whereas CFL numbers 1 also tends to blow up the simulation at the very starting. So this might have to do with the initialization. And finally, a large initial viscosity ratio also causes the numerical issue. And this is the main cause that leads to a under prediction in the turbulence length scale. And looking into this. In conclusion, so the velocity, turbulence, energy are in pretty good agreement with the experiment. Both mass flow rates and total pressure ratio matches the experiment within an error. But we are underestimating the turbulence length scale using the SU2 solver, and it's due to the problem with the omega. We're still looking into this. Several parameters that could affect the stability, including quantities, the type of limiter, and the CFL number. And this will conclude my I would like to acknowledge FAA for funding this project, and the hosts are collaborator on Raytheon Technology Research Center for the support, and the SU2 Foundation for providing the code and support. Thank you, and I am now open for questions and suggestions, and advice is also welcome. Thanks.
Right. Thank you very much, Nuo, for this nice presentation. Are there any questions from the audience or live? Yeah, Josh.
When you said one of the mesh requirements and use a wide book size less than equal to 1, we ever tried using it in an all function?
I'm sorry.
Could you hear it? So the question is, if you ever tried wall functions because of this y plus 1 requirement.
Have I ever tried the wall function? No. I did not use the wall function, and so far I have been trying to resolve the wall using a small y plus.
Yeah. So maybe you can try it and see if it helps.
Yeah, that's a good point. Okay. Yeah.
Yeah. So another question from Akin. Yeah.
So you use point wires to mesh the fan? So, so Pointwise has a photo machinery module now? Is it like autogrid or?
So how do I mesh the how do I create the mesh using PointWise? That's a question like for turbo machinery application. Was that, did I get this question correct?
So if the question is if Pointwise has turbo machinery capabilities. Did you remember?
Well, I believe there isn't a specific turbo machinery module in PointWise, but the way I measure this, I simply import the database into PointWise, and then I choose one of the blade passage, mesh it, and PointWise has the option of creating a periodic surface or periodic domain, and this is how I did it. And then I basically draw the multi-block structure. Basically, I draw them by hand.
Okay. Great, thanks.
All right.
A simple question. What is the objective of this simulation exercise? What problem do you solve?
Yeah. So what is the objective? So there are a couple of the objectives that we're trying to, like, couple of goals. So one of the things is that we use a RANS informed acoustic models to solve for the broadband interaction noise. So using this type of model, we do require the inflow velocity and turbulence quantities, so like turbulence intensity and length scale. So that can only be solved using a RANS simulation, which is the cheapest, or it's the considered a cheaper option compared to like a LES, like a high fidelity LES simulation. So that's one of the that's one of the main goals that we're trying to do.
Hey, thank you.
All right. If there are no other questions, then thank you again, Nuo, for the presentation.